we just went over a poor bending, very poor bending on the member, only the bending moment apply, no shear force, no normal force, as you can see there, and it will display the shape as shown. And from the poor bending, we also know there is a linear strain distribution along the cross section. And now let's investigate what happened to the stress, right? So let's talk about in terms of normal stress. What do we have? So we already assume, as you can see, for assumption here for the poor bending, let's make a few more assumptions before we explore what is the normal stress in a poor bending. So let's assume, in addition to the previous four assumptions, we want to assume the material in the bodies are homogeneous. It means same material throughout, isotropic, same property in all dimensions, isotropic, and then linear elastic. Linear elastic. So what do we have? If it's linear elastic, homogeneous, and isotropic, I have the Young modulus or modulus of elasticity is equal to sigma over epsilon. And from that, I have epsilon equal to sigma over modulus of elasticity. So with that same equation, we can apply for the epsilon at y position equal to sigma, the normal stress at position y at the firebolt divided by E. For your of you don't follow, that is the y we define, delta C, delta y, etc. in that finger. So from here, what we have is delta y over E and sigma y over E. So from that, we also have normal strain at the outermost fiber is equal to the normal stress sigma C over E. So from that, we can plug into that equation. Here, epsilon y over y equal to epsilon C over C. With that, we can have plug epsilon y, it's sigma y over E, and we have y in that equation. I plug it in right there, equal to sigma C, and we have E Young modulus times C. And now E the same, so we can cancel out. You can cancel out, so we have it sigma y, which is the normal stress at the position y distance from the neutral surface, and then over y it equal to the normal stress at the outermost fiber divided by the distance from the neutral surface to outermost fiber. So let's box that relationship again, and as you can see, compared to this, they are similar, right? Just replace epsilon y, epsilon c with the sigma y, sigma c, normal strain with the normal stress. So with that, what do we have? We can have the same conclusion, but with the assumption that it's linear elastic. So that one, we can have for elastic behavior. Why elastic? Because that we can have equation E equal to sigma over epsilon for elastic behavior. Stress. Stress. E linearly distributed. E linearly distributed. So how can we draw it down? So it's similar to the strain that I draw there. We can have the member and then the neutral surface. Neutral surface. So if we have a moment apply counterclockwise in this side, and as you can see with the demonstration, it will cause the tension on the bottom and compression on the top. So from here I can have the normal stress get maximum at outermost fiber 0, in the neutral surface, and similarly the bottom one, similar to the bottom one, the top one will be the same, but it will be in compression as you show with that moment. The top it will be compressed or contraction, the bottom will be in tension or extend the length of that. So that's why with the normal stress are changing the direction. So from with that moment, so we have that is sigma and in tension at the bottom, and of course the top we have sigma in compression. So what does that mean? With the same cross section, with the poor bending moment applied on that, it creates within that cross section both tension and compression, which is unlike the actual load. It will create the either tension or compression. Yes, create both in the same cross section. So keep that in mind. But whatever happen, it will be the stress is linearly distributed for elastic behavior, and it will be 0 at the neutral surface, and it will get the maximum at the outermost fiber, either compression on or tension as shown in there. So with that, move on to the with that stress. What we can say about the internal forces with that stress for the cross section? What if I cut that member with the poor bending? What should be the internal forces? So internal forces. So for internal forces, let's draw a very big in here with the cross section in 3D for now. So we have that 3D, and assume this one it can be a rectangular cross section. Rectangular cross section. And the neutral surface, the drawdowns, and because that is a rectangle, the neutral surface it will be go through the middle, the centroid. And if you see that here, it will be a hidden neutral surface on the other side. And of course, it will be hidden for that member in here if we draw it in 3D. So what do we have with that moment here? If I put it in 3D, the bottom it will be in tension, so we can have and maximum at the outermost fiber, so it get maximum here, and it will be 0 at the neutral surface, 0 at the neutral surface, so we can have here and get 0. And similarly, we have that maximum at the outermost fiber and 0 at the neutral surface. Similarly, the top one, we also have sigma maximum at the outermost fiber, but it all in compression, so it get into the cross section, as you see there, get into the cross section, and it also go smaller and then get zero at the neutral surface. Go smaller and get zero at the neutral surface. Go smaller there. So from that, if we call the top one is compression, so that is sigma c, make it for compression, and the sigma t for tension. Then the sum of all the stress, as you can see, it will be called that either the force Fc, the force Fc, which is go into the cross section, the compression force, and the bottom half, it will create the tension force that go out of the cross section. We call it Ft, and because it's poor bending, as you can see, we don't have normal force, shear force, so they have to be zero. What does that mean? We have the sum of all the force along the x-axis, which is the longitudinal axis, have to be equal to zero, because for the cross section it only this one is poor bending, only moment, no normal force, so the sum it have to be zero. What do I have? So it means that Ft minus Fc equals zero. So what does that mean? The sum of all the force at the tension have to be equal to sum of all the force due to compression. So keep that in mind to get a poor bending, no normal force in one cross section, because the portion create the compression should be equal to the portion that create a tension. And then from that we can have the moment and stress relationship in here. So that is the internal force. What is the moment and stress relationship? So the next step, we want to find out the moment, stress. So with that, poor bending, it will create the normal stress. But how the relationship can be realized? That's very important. With a certain moment applied, how can I know the normal stress distributed in throughout the cross section as shown here? Okay, so that this is moment stress relationship to address that one. So as we already know, for moment, it equal to the force time the perpendicular distance or moment arm. If we get any small portion on the cross section, at position y, and if we integrate throughout the cross section, you will get the moment applied on that section. So with that, we can make the integral of all of that throughout the cross section. So what do I have? If that one, we can have throughout the cross section, that we call it cross section A, area A, y, any random y, and then at y, at the position y, from the neutral surface to the point that we are talking about, time the force, and as you recall, the force is equal to the area time the normal stress, sigma y normal stress, time the areas at that point, delta A. And with that, if we apply for a linear stress distribution, which is true if it elastic behavior that we are doing now, if it linear stress distribution, so what we have, we will have m, and we write at integral throughout the cross section y, and then sigma sigma y. What do I have? From that equation here, sigma y equal to over y equal to delta c over c. So if I plug in, I kick y on to the right, so I have sigma y equal to y delta c over c. Everyone see that? So we can plug it in here in that equation with the sigma y equal to y sigma c over c, and then we have dA. And sigma c at a certain moment applied, the outer sigma, the normal stress at the outermost fiber remain unchanged. So that we can bring out c is the distance from the neutral surface to the outermost fiber. If it constant cross section, then c also constant. So from that I can print that out. It will be equal to sigma c normal stress at outermost fiber over c the distance from the neutral surface to outermost fiber, and what left in the integrals is y squared dA. So now recall in torsion we have, and I write down but I'm going to erase, we have something called integral rho, which is the radial distance time dA. And if you recall what we call that integral, polar moment of inertia J. Everyone recall that, right? And that go to the reference. We can have that pi over 2 radius power 4 if it cross section. Recall that. Now, as you can see, it's similar to this case. We don't call that a polar moment of inertia, but now we call that the area moment of inertia. If you recall previous lesson that we have, so let's recall area moment of inertia here. So if you recall area moment of inertia, and you practice that in lesson 6, right? Inertia before buckling. So here we have I, that is stand for area moment of inertia. J stand for the polar moment of inertia. Basically that we already learned, I square dA integral. So from that, for example, if the rectangles, so we have it parallel power 1, perpendicular power 3 divided by 12, if you recall that in the appendix. So from that one, we can rewrite the moment equation. So from that we can have moment equation is m. Now this one equal to I. This one, this portion, now equal to area moment of inertia. So what we have here is equal to sigma c over c I. That is the moment. And then from that one, I also have sigma y. If I replace sigma y equal to y sigma c over c in that equation, I also have that equal to m moment times the y, the distance from the neutral surface to the point that I'm interested, over the area moment of inertia. So that are the two very important equations for today's class. So the first equation, we call that either flexure formula, flexure, because it's called the flexion, right? Flexure formula, relationship between the moment and the normal stress. So with that stress, normal stress, I can find out the associated moment. Now, given the moment applied, I can find out the stress, normal stress, at a given point on the cross section, right, from the neutral axis. So this basically the normal stress at y by definition at you here. Y from where? Y from neutral surface. Okay, from the neutral surface. Very important. So by definition of y from neutral surface there, you can have it here from that y from neutral surface to the point of the interest. So if it y equals 0, what can I say? Y equals 0, it means that at the neutral surface, then the sigma y equals 0. That's show it in here. You see the stress at the neutral surface equals 0. Stress at the neutral surface is equal 0. If y, the maximum they can get is C, which is from the neutral surface to the outermost fiber, then the maximum of the normal stress is at the outermost fiber, either top or the bottom. Everyone see that there? So that is, we call it moment and stress relationship. So before we continue, we work on worksheet 8.8, and then we go to the beam design later on. So let's practice worksheet 8.8 first.